Hello everybody. We are going to be continuing our discussion on methods of analysis for general loadings. Last time we looked at last two times we actually looked at the Duhamel integral approach, which is a time domain approach, and we looked at the Fourier transform approach, which is really a kind of extreme representation of the periodic load, excepting where the periodicity, which is the time period of repetition, the periodicity is considered to go to infinity. In other words, it is really an arbitrary load, but arbitrary load, once it is considered as a periodic load, then you can we establish that you can develop the Fourier transform. Now, these are all integrals, and especially the Fourier transform, if you look at it, it is essentially a complex integral. So, obviously, these although they look very elegant in presentation, in reality if we have to solve them, we have to go about some other approaches. So, what we are going to be looking at in the next lecture is to really continue looking at a numerical analysis of response, because the integrals that I have shown in reality can never be solved excepting unless you know the form of p of t, and typically what you have given is essentially nothing but the following this thing is that you are typically given let us take that this is some form of the load. Again, I mean, I am showing it on one side, we will see later on that there are situations in which you have both directions. So, let us take something of this where this is 0 and time duration. Okay. So, what we in general have is essentially in today's world, most data is stored in digital form. In digital form, what you have? You essentially are given, look, this is you have delta t, which is like a fixed time interval. There are two aspects to this delta t, and we will discuss this as we go along, but there are two aspects. One, it should represent the load appropriately. So, one thing about delta t is that it should represent the load properly, and it should also represent response. So, therefore, delta t is typically taken in such a way that it should represent both the load and it should represent the thing, and what you have is at delta 0, delta t, 2 delta t, 3 delta t, 4 delta t, what you have is P 1, P 2, P 3, P 4, P 5, or you can call this as P 0, P 1, P 2, P 3, P 4 to keep it. So, in other words, at n delta t you have P n, and T d is equal to n into delta t. In other words, there are total n number of records, n number of values in any record of the loading. Okay. That is typically what you are given. Okay. And as I said, what should be delta t? Well, delta t should be, it should be small enough to represent the load properly. In other words, if you have a load like this, okay, typically delta t should be small enough that it takes all of these, represents each part properly. And secondly, delta t should also be small enough to represent the thing. Now, how should it represent the load? The load is not typically if duration is of the order of about 30 seconds, okay, delta t is typically of the order of 0.005 seconds or 0.01 second. Okay. So, this kind of representation delta equal to 0.005 or delta equal to 0.01 second essentially typically represents most loads. Of course, if you have blast loads which last for microseconds, obviously delta t will have to be blast load typically lasts milliseconds. Okay. In such situation 0.005, which is essentially 5 millisecond, okay, a delta t does not make sense, because if your blast load lasts for 5 milliseconds, obviously your delta t has to be significantly lower than that. But for other kinds of loads other than blast loads, typically delta t equal to 0.005 or delta equal to 0.01 is good enough for representing the load. How should we represent the response? Typically, if you look at the fundamental time period of the structure, delta t should be less than t upon 10. Okay. These used to be the in other words, what does that mean? That means is that one cycle of response, okay, this is like one cycle of response. If it is a single degree of freedom system, if a single degree of freedom system, one cycle of response is t, and if delta t, in other words, we should at least have 5 representations. This used to be the old way of looking at it. It is no longer valid. This is required for stability for some numerical methods, but typically delta t should be a significant number. Well, I will call this number some p or something, which is of course an integer, okay, but it should be significantly large. And this typically, if you have a single degree of freedom, I would not say 10, I would probably say that you should have at least 10 in this lot. So, p should be about 20. But that is for single degree of freedom. Okay. So, in other words, essentially delta t has to satisfy both the representation of the load and the representation of the response. Anyway, so that is, but typically this is not in your hand. This is more for the representation of how delta t should be done for numerical analysis. But representation of the load is typically done in a format which is the measuring equipment's time interval, the maximum. For example, let us say that a measuring data acquisition system has a maximum of 200 samples per second. If it has a 200 samples per second, automatically if it is doing it at 200 samples per second, what does that mean? It means essentially delta t is 0.005, because you are getting 200 samples per second. So, delta t is automatically set. I have some, we will show you when we go to the lab, we will show you that there are some data acquisition systems that can do it at 1000 samples. In other words, delta t is measurable at 0.001. So, in other words, let us be very clear. What we are doing here is looking at, for the numerical analysis, this part delta t, okay, may be different from this delta t, because this is more digitization. Now, how if we digitize, should we get this? Well, there are ways and means of doing it. Sometimes it is called downsampling. For example, let us say you are doing it at 1000 samples per second. So, you are picking up at 0.001 second, right, but you do not want to do the analysis at that, you want to do analysis at this. So, then what you do is you take this load, okay, and you pick up every fifth representation of the load, okay, and that is how so those are things that there is a difference between measurement of load, okay, digitized record of the load, and the delta t that you require. So, these are two different, but for now let me just not get too much caught up in how the measurement is done. Let us just assume that even if I have downsampled it, I have got it in this form. This is the form that is at the delta t that I need. So, how do I now proceed for this? The first thing that I am going to do before I go back to the time, although I started with the Duhamel integral and came to the frequency domain, I would first like to do the frequency domain, how we do the numerical analysis, frequency domain analysis, because that is typically more used in today's world, purely because if you have a linear system, okay, principle of superposition is valid, and then frequency domain analysis is a far superior and quicker approach, a more computationally efficient approach for solution of response, purely because in the frequency domain, if you remember, the convolution integral, which is the Duhamel integral, basically transforms into a product, a multiplication, albeit it is a complex multiplication, but it is still a multiplication. Okay. So, that is a more trivial approach. So, now I am going to really talk about how when you do Fourier transform, the Fourier transform, how do we do it in reality? Okay. And that approach is called, as I mentioned in last time in passing, it is called the discrete Fourier transform. So, that is DFT, and FFT, which is the fast Fourier transform. Everybody would have heard today that, oh, I did a FFT of a signal. Well, what is an FFT of a signal? It is actually a Fourier transform. I have done the Fourier transform. I have taken load PT and transferred it into the frequency domain. And the reason, again, remember, I put p I omega, not because p is just to show that p is a complex function of omega bar. Okay? That is all I am trying to show. So, essentially this procedure going from here to here is the Fourier transform, and so we use the discrete Fourier transform. I will essentially write down the discrete Fourier transform, and the FFT, which is developed by Cooley-Tuckey at IBM lab, was essentially a faster way of doing this DFT. So, I am not going to spend too much time on the FFT, because the FFT is really a mathematical procedure which does not add to our knowledge. I will leave it up to you to read the original paper by Cooley-Tuckey, which appeared in in 1962. Okay? But you really do not need to know it. If you know the discrete Fourier transform, you know the basic information that you need to put into any FFT routine or FFT analyzer that you need to put use today, because typically FFT analyzers are black boxes. But there are some fundamental aspects that you need to consider before you do the Fourier transform. Okay? So, now the thing is, what is a discrete Fourier transform? We are essentially saying that, look, this integral, which was the integral minus infinity to infinity, which is p I omega, which is equal to, what was it? P of t e to the power of I omega, sorry, P of tau I omega t minus tau I t dt. Okay. So, this there is no tau here, it is just t. Okay. The t minus tau comes in the Duhamel integral. So, essentially again I am going to rewrite this, I omega bar is equal to t going from minus infinity to infinity, P of t e to the power of this is the frequency domain representation of the okay. And the other thing that you have is this is the Fourier transform, and again I want to rewrite that P of t is equal to omega going from minus infinity to infinity 1 over 2 pi P I omega e to the power of I omega t d omega. This is the inverse Fourier transform. Okay. So, essentially what I am doing right now is putting down this particular form. Now, if I do a discrete Fourier transform, what we are essentially doing is we are going to solve this problem and these problem by doing what? A summation. In other words, this will become delta t, this will become delta omega, okay, and that is how we are going to do it. And how would we do it? Okay. Now, the only way to do it is by saying that look, T p which we took, remember periodicity which we took as infinite is not infinite. In other words, what I am saying, and this is very important to understand, that if I have any load and I have this T p, okay, where this is T d, duration of the load, T p is always significantly greater than T d. Okay. And so, I am assuming that there exists another and there existed another, and there will be like every T p, this is T p also. Okay. So, T p is much greater than the duration, okay. That is our assumption. If we assume that, then essentially what are we saying? That okay, if I am doing a digitized, I will say that look, T p I am now going to define it as n delta t. Okay. In other words, this duration is put into n. There is another thing, and that is delta omega 0, the lowest frequency that I can represent is going to be equal to okay. That one, since T p is large, I will call this as my delta omega bar. Okay, because if T p tends to infinity, this becomes d omega bar, right. So, in other words, if T p is large, this becomes my delta omega bar. In other words, if you really look at it, delta t represents my, what does it represent? It represents my time resolution. And delta omega bar, if you note it, if this is delta omega bar, once, in other words, I made it a periodic load. If I made it a periodic load, what do I have? I will have the largest frequency is going to be equal to m times delta omega bar, omega n. Because, in other words, if you look at it, what I am doing is I am discretizing delta t, okay, t from minus infinity to infinity. Now, obviously, it is never minus infinity to infinity. In this particular case, it becomes then what? It becomes 0 to Tp, right, 0 to Tp, okay. And if you look at this particular one, or it could be like minus Tp to Tp by 2 or something of that sort, where we break it up, but those are not issues. It's typically 0 to Tp, okay, because that's the kind of time frame that I'm looking at, okay. And this one essentially then becomes what? It becomes now omega, note that omega has to go from minus infinity to infinity, because for this representation to represent, you require both plus and minus, and delta omega essentially represents my frequency resolution for this integral. Okay. So, this is a very, very interesting point to be noted, and that is that I have the discrete Fourier transform. I am going to take the Fourier transform. In other words, I am going from p t to pi omega. This is the process that I am doing. If I do that process, what does it happen? It basically is pi omega bar becomes equal to now summation n going from 0, right, because it starts here. So, that is 0 here, and it goes up to n, right, because this is n, okay, but this becomes then what? It becomes, if Tp is n, then this becomes 0 to n minus 1, because if this is the thing, okay, there is n, because you will start at 0 t and this ultimately becomes n. So, that you go from 0 to n, actually there are n plus 1 numbers. Okay. So, you go to from 0 to n. Now, if you really look at it, it is p at t n, right, e to the power of I omega t n, because you note that this is all n. So, this p t n, p at t n, okay, e to the power of I t n into what? Into delta t. That is what we have, right. So, now the thing is that note that T n is equal to n delta t. Okay. So, if you really look at it, this becomes what? E to the power of I omega bar into n delta t. Okay. So, if I really represent this properly, then I get the following form. Let me just write that form for you. I get the following form, and that look at it, that I have p at I. Now, the question then becomes that, look, even this is, I can't do p I omega bar, because again I am actually finding out p at I omega bar m, right. Why? Because if I am doing a frequent and I have essentially, what do I have? I have n going from 0 to n, and I have p of n delta t, that is the p that I am picking up, and here I have e to the power of I omega bar m, okay, n delta t into delta t. Now, the question then becomes that you see even the frequency domain is being transformed into this. Now, note, so therefore, what we have is frequency domain has delta omega bar, 2 delta omega bar, 3 delta omega bar, blah 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 blah, till I hit m omega bar. Now, note that there are these issues that for every delta omega bar I have a minus delta omega bar, minus 2 delta omega bar, 3 delta omega bar, blah blah blah, and a minus m delta omega bar. So, I have to have all of these. Okay. Now, the question then becomes is the following, that can I just look at one side, because you see I have certain aspects which are very very important, and that is that if I have both real and complex, okay, then this part is a complex term, but it actually goes and represents a real term. Okay. And since this one has, so how many values does it have? If you look at it, there is a 0 value. Okay. How many discrete terms do I have? If I have n, see T p represents n delta t. So, in other words, I have n T p terms, n delta t terms. So, this time domain is this. If you look at it, okay, we can look at this particular one. How many terms are there? There are n plus 1 terms in the specific one. Okay. Now, if I take the 0 term out, you are essentially looking at n terms. Now, in the n terms, you will have to put in these many terms. So, if you really look at it, delta t in a way represents pi upon the Nyquist frequency. We call this the Nyquist. This is the largest delta omega bar that can be represented in this system. Okay. So, that if you look at it is equal to what? You have 2 m terms. Okay. So, therefore, omega bar Nyquist 2 m terms has to be equal to n. Okay. So, the Nyquist then becomes essentially 2 n terms have to be present. Now, look at it, if you really look at it strictly, it should be 2 pi upon delta t, right. But you see, because you have to have plus and minus, essentially this becomes, you would think of the largest if there was no known minus, right, and these terms n and m have to be the identical values, because they represent the same. Then what would happen? You would have a situation where if n was equal to m, okay, then what would be the highest frequency? Well, if that would be n into delta omega bar. Now, n is the lowest frequency, delta omega bar is equal to 2 pi by t to 2p. Okay. So, 2 pi by Tp, Tp is equal to what? Tp is equal to 2 pi upon n, Tp is equal to, yes, n delta t. So, if I put this up, what does delta t becomes? It becomes 2 pi upon n delta omega bar. Now, if you really look at it, if you only had one of them, okay, m was equal to n, then what would be the highest frequency? Well, the highest frequency would be n delta omega bar, there is no doubt about it. But see, because you have both, it is actually n by 2 delta omega bar, which is the largest frequency that can be represented in this, and this is the one that is called the Nyquist frequency. So, if you just substitute that in here, okay, this is the largest frequency, this is the Nyquist, okay, omega bar, and if you really look at it, omega bar Nyquist, therefore, substituting this into this, okay, n delta omega bar becomes 2 pi n delta t and upon 2. So, this becomes pi upon delta t. Okay. So, one aspect is, so the n, what should be Tp is determined by delta t and the number that you want. And how do you determine this number? Well, this number has two parts to it, and one part which is that, look, in the frequency domain, okay, delta omega bar is equal to 2 pi upon n delta t. So, 2 pi upon Tp should give me sufficient. So, Tp should be large enough such that the frequency resolution is good enough. On the other hand, the delta t that I choose, automatically determines the maximum Nyquist frequency that I have. So, if you look at it, I talked about essentially the following thing, and that is that, look, delta t is equal to, let us say, 0.01 second. If delta t is equal to 0.1 second, then delta omega bar becomes pi upon 0.01, and the frequency resolution, which is equal to delta omega upon 2 pi, essentially becomes 1 upon 2 into 0.01. So, it becomes 50 hertz. In other words, if you do delta equal to 0.01, the maximum frequency that can be considered in the analysis is 50 hertz. Now, if you know that that is not good enough, what do you have to do? You have to take a smaller delta t. For example, if you take delta t equal to 0.005 second, then this is not delta f, this is the Nyquist, f Nyquist. Okay. So, then f Nyquist would be equal to 100 hertz. Okay. So, therefore, Tp determines delta omega bar. For example, I would call it, although delta omega bar is circular frequency, I will represent it by f, because this is something that we know. Okay. So, now Tp has to be large enough. Let us say, how long should it be? Well, what kind of frequency resolution do I want? Well, if I am going to have a Nyquist frequency of 100 hertz, I would probably like a 0.5 hertz delta f. If delta f is 0.5 hertz, what does Tp have to be equal to? Tp by definition has to be 2 seconds long. Okay. So, typically, if you are looking at the typical kind of things in which you need these, okay, your time duration. See, note also that Tp, by the way, has to be greater than Td, right. So, therefore, what do we have? Well, we have this situation where Tp is typically, if Td is of the order of about 20 seconds, Tp should be 20 plus. Now, what additional things have to be there? Well, let us go back to that. Remember? Well, this is initial conditions at rest, and that is the one that you are doing. Now, when you are taking this, it implies that this will give you certain aspects. So, therefore, now if it is a single degree of freedom that you are looking at, I know that I will require some I times T, where T is the free vibration time period of the structure. Okay. And what I? Well, I will depend on what? On xi, because remember, this is free vibration. If I have free vibration, remember that e to the power of I omega t. So, I need to see that the previous one's free vibration with a particular Td, UTD and this thing does decrease down to small enough. Okay. So, I is always dependent on xi. If xi is small, I goes up. If xi increases, I goes down. Okay. So, therefore, Tp is typically of the order of about, if you have a time period of about 1 second, okay, Tp would typically be of the order of about 40 seconds for a xi equal to 5%. Why? Because 20 cycles of 5% brings it down to a sufficiently small value such that errors are not introduced. So, if Tp is 40 seconds, then automatically delta omega bar is equal to what? 1 over, sorry, delta f bar is equal to 1 over 40 seconds, which is equal to what? 0.025 hertz. So, in other words, this thing is automatically set at 0.00 hertz, and if you are doing 0.01 second and you have got 40 seconds, n is equal to what? N is equal to 4000. Okay. N is equal to 4000. Well, what is the Nyquist frequency? Well, we know delta 1, okay, 0.01. It basically means Nyquist frequency is 50 hertz. 50 hertz, 2000 points, well, 2000 points and minus 2000 points, that makes it 4000 points. So, you see how the entire thing matches up. So, essentially you have to worry about the frequency resolution and so your Tp is determined by frequency resolution, and delta t to a certain extent is determined by the Nyquist frequency. Nyquist frequency means, well, how many frequencies do I want to consider, and those are issues that come from practice and also knowing what kind of structure there is, what kind of load that I have, what Nyquist frequency should I take. Those are not issues. All I am trying to say is that typically the value n is known. Okay. And also understand that what this means is that T n is equal to n times delta t. Okay. And you see, so therefore, n times delta t, and delta t is equal to Tp upon n. So, if you really look at it, this becomes n Tp upon n, that is my Tn. Okay. Similarly, if I want to look at omega bar m, that is equal to m into delta omega bar. Okay. So, I have a situation where my P into I omega bar m is equal to, now doing the summation 0 to n, okay. And what do I have here? I have P of T n. Now, P of T n is equal to what? P of T n is equal to T n, where T n is this, it does not matter, but more importantly is the exponential term. Exponential term is what? It is equal to, I have minus I. Now, omega m is equal to m delta omega, right. Now, delta omega into T n, T n is equal to n T p upon n. Okay. Now, let us look at what T p is equal to. T p is equal to what? We had already said it, delta omega bar is equal to 2 pi upon T p. So, T p is equal to what? 2 pi upon delta omega bar. So, this is my term, okay, into delta t. Now, I can take this delta t outside, because this delta t is not a function of n. So, this can go directly here, and note that T p is 2 pi upon delta omega. So, if I plug it in here, what do I get? I get 2 pi upon delta omega and delta omega cancel out. So, what do I have? I have P I omega bar m is equal to delta t n going from 0 to n P of T n into exponential of minus I m n, okay, and there is a 2 pi. So, into 2 pi upon n. So, this becomes I 2 pi m n upon n, and that is my omega term. You see, this is the discrete Fourier transform. Now, so therefore, n is defined, and once n is defined, note that how many terms I have, okay, will be determined automatically by this. And if I look at the flip side, if I look at my P t, okay, the inverse. So, this is my discrete Fourier transform. Now, if I want to look at the inverse Fourier transform, okay, if I look at the inverse Fourier transform, what do I get? Well, the inverse Fourier transform is what? P of t upon 2 pi omega bar minus infinity to infinity, okay, P of I omega bar into e to the power of I omega bar t d omega bar. So, this becomes then P t is equal to delta omega bar comes out. So, it becomes delta omega bar upon 2 pi integral. Now, if you look at this, this becomes m going from minus n, no sorry, m going from minus m to m, okay, because frequencies have both sides, okay. P I omega bar m, which I know is m into delta omega into e to the power of I omega bar t. Now, I already know what this looks like. This is 2 pi I m n by m from the previous term. This is my inverse discrete Fourier transform. And I know that, look, m is equal to n by 2. Okay. I know that m is equal to n by 2 because note that I mean this is T n, by the way, obviously this is at T n. Okay. So, I have a situation where T n is equal to p I omega bar. So, this is the inverse discrete Fourier transform. Now, the only thing that happens is that, remember that T p delta t and omega bar Nyquist. Actually, delta t is not in your hand, it is T p and these, which are typically the design parameters. Once you have this, and look, this is we always look at this as delta f. You look at, if you look at this is nothing but delta f. Okay. So, you are looking at Nyquist frequency, and I mean, if you look at f Nyquist is equal to m times delta f. Okay. So, these are the Nyquist frequencies. As I said, 50 hertz, 100 hertz, this is something that I know. This is something that I can define. If I define this, automatically delta t becomes equal to 1 upon 2 f prime Nyquist automatically. This is something that delta t we know. Once we know delta t, I can find out n. Now, so in other words, if I were to review the frequency domain analysis, it is that, look, what are the things that I know? I know T d. This I know because I know the duration of the load, okay, and I also know the digitization. Okay, that does not matter. Okay, I know some other term I'll use. Probably I'll use delta tau. P delta tau. Okay, 0 p 0. These are the things that I have, but delta tau is really the digitization record. Then I know time duration. Okay. Once I know time duration, look, I am going to be doing it for a structure. So, I know T and I know xi. Okay. I have a load with a duration, fixed duration, and I have a structure where I know the T and xi. Once I know T and xi, I know that because I am going to make it a periodic load, I need a sufficient number of zeros. So, in other words, I am given this record up to T d. This record I have. This is the record of P t. I have this record. Now, what do I have to do? T p is not T d. T p is greater than T d, and typically T p is equal to T d plus I t, where I is a function of xi. Okay. So, from that, given T d, I can find out my total time that I need to put in. Okay. I also know my Nyquist frequency. How I know my Nyquist frequency, let us not worry about it right now. we will come to that towards the end of the course. If I know my Nyquist frequency, I know my delta t is equal to, sorry, this is wrong, delta t is equal to 1 upon 2 f Nyquist. Tp delta t, once I know that, n is equal to Tp upon delta t. Okay. So, I can find out my discrete. Now, I just want to end with the fast Fourier transform. The fast Fourier transform is nothing but the discrete Fourier transform, where n is a function of, is a power of 2. In other words, n can be 1024, okay, 2048, 4156, or typically up to 4096, okay, or 8192. Anything more than 8192, you are dealing with numbers which becomes very, very large. So, that is all that is, and then what happens is, this is the minimum Tp, okay, and then what you do is, delta t, delta t from this, okay. So, once you know delta t, all you do is you take 2 to the power of r, I mean Tp is equal to 2 to the power of r delta t, where this Tp that you define 2 to the power of r delta t is more than this minimum value that you require. And that in essence is the discrete Fourier transform. So, two parts. One is that you should know your Nyquist frequency. Once you know your Nyquist frequency, you know delta t. If you are using the fast Fourier transform, you have to use a Tp which is slightly larger than delta Tp minimum. So, if you know Td and you know I of t, which is a function of xi, I, the minimum number of cycles to reduce the error, okay. And I mean, because remember the previous one has to die out, initial conditions have to be as close to as rest as possible for the Fourier transform for me to give me an accurate estimate. Okay. So, this in essence is the procedure that you follow. So, you always have to put in what are known as trailing zeros to build up a period after the duration. This is most important. Okay. Thank you very much.